Welcome to our review on electromagnetic waves and matter. Now, the first thing that we really need to understand is how to draw a ray diagram. Hopefully this is something you did do all the way back in Key Stage 3, so that what you've done in your GCSE is just a reminder. But just in case, ray diagrams are used to show those key behaviours of our actual rays, so reflection and refraction. So a few key points to remember when we come to draw our ray diagram. First of all, use a ruler. Do not try and draw this freehand. It will not go well for you. Secondly, use a pencil. If you make a mistake, you can rub it out. You only get the one version of the diagram on the exam paper, so don't do it in pen. And then if you make a mistake, you're kind of stuffed. So always use a pencil and a ruler. When we're actually drawing the rays, then that is a straight line. When we actually come to draw our diagrams, obviously it depends on what we're drawing as to how it's going to be set out. So if we consider reflection first of all, the top diagram there, then what we can see is that we've got our angle of incidence at the top. Now that's the angle between our normal line and our incident ray, the one that comes in. So your normal line is at 90 degrees to the actual mirror. So what we do is we have our angle of incidence measured, and then on the other side we measure the exact same angle, and then we know our angle of reflection, because hopefully you remember that the angle of incidence is the same as the angle of reflection. Once you've done that, just put the arrows on to show the direction. Go careful when you're doing this though to make sure that number one, the rays meet and they meet on the mirror. Don't cross them over or have them meeting a little bit in front or just not meeting at all. So just go careful and take a little bit of care over drawing that diagram. The bottom one there is showing us refraction, which is the bending of our light. And what we have, still our normal line at 90 degrees to our surface. Our angle of incidence, again, between our incident ray and our normal line. But as we're going from air into our glass block, then what happens there is it's going to bend towards the normal. So the angle of refraction is obviously going to be lower than the angle of incidence in that case. But again, add the arrows to show the direction it's moving in. As we've seen previously in this topic, then when sound waves change speed, then they're refracted, so they change their direction slightly. What we now need to look at is what happens with light. So if we have light that's entering a denser medium at an angle, as you can see in the diagram on the right there, then it's going to slow down and bend towards the normal line. So you can see the normal is that red line running sort of vertically through the block itself. Then as our light comes in at the angle, what's going to happen is that one side, the side that hits the glass first, slows down first, and then it's going to bend that light towards the normal, as you can see in the diagram. What we then find is that when we consider the density of the mediums that we're going from and to, the greater the difference in density between them, then the greater the change in direction will be. So you're probably sitting there and thinking, why do I really care about this? And the key reason that we do care about the ability of our waves to be reflected and refracted all comes down to the fact that when we're trying to transmit waves over large distances, there's a big problem. We live on a planet that is curved. So as soon as you try to transmit it over a large distance, the curvature of the Earth kind of gets in the way. So what we can actually do is by using these behaviours of our actual waves, we can transmit them over a much longer distance. So if we think about radio waves first of all, so these are the ones which are less than 30 megahertz, then what we find is that we can reflect them from a layer in our atmosphere called the ionosphere. So any electromagnetic wave less than 30 megahertz in its frequency will be reflected by the ionosphere, which means that we can send it up and then bounce it down just from one of those layers in our atmosphere. If we have these waves that are more than 30 megahertz, then what we're going to do is that's going to be able to pass through the atmosphere, and that's where it's going to intercept with one of our satellites that we've put in orbit. That then allows us to bounce it back down to a different part of the Earth. And that's what we do in terms of our high frequency radio waves and our microwaves. So we're using those for the satellite communications. When we're thinking about our electromagnetic waves, the last thing we really need to consider is what happens in terms of transmission and absorption. And the answer is it's all dependent on their wavelength. So if we consider a couple of examples just to help you get this into your minds, then if we think about sitting in our house, what we actually need in order for us to be able to see outside, we've got to have a window, because visible light can't pass through the brick walls of our homes. However, what we do find is that we can use things like our phones and TVs inside. And the reason for that is that the walls are able to transmit radio waves and microwaves, but things like visible light and ultraviolet are absorbed by the walls. If we consider a second example of the atmosphere, it's very useful to us because it's going to actually absorb X-rays and gamma rays, which would normally be very harmful to us and other living things on the planet. So the fact that our atmosphere absorbs those two types of electromagnetic waves is actually incredibly useful to us. Hopefully at the end of this video you can now describe how to use a ray diagram to show reflection and refraction. You can explain why EM waves are refracted and describe the different ways that EM waves will interact with matter.